everybody. My name is Adam Evangelista. I'm a fourth year mechanical engineering major. I was working on the Robotic hand project this past year along with my colleagues up on the board. Luke, Newton, and Gabe, they graduated last year, or Bruno graduated last year, and Gabriel couldn't make it here today, so he stuck with me for the hour. So context, the robotic hands, there's a lot of interest in putting human hands in places where they shouldn't be, right? There's a few examples up here. For example, there's the Robonaut 2, which is from NASA. This idea of a kind of robotic astronaut that you could use up in space in dangerous environments where you wouldn't normally have a person. Are you guys familiar with the Da Vinci surgery robot as well? You want those tiny little hands in places where you can't put them, so you want a robotic hand that you can operate remotely. And so the idea is we'd be able to protect more people and be able to do more dangerous things as the robot technology gets better. Cool. Another. Specifically, when we picked up this project in the group last year, they were interested in hazardous waste and hazardous environment handling and manipulation. And so some of the areas we decided to focus on that we were interested in was submarine environments, radioactive parts and waste management, space, flaming buildings, and just high temperature environments, which we'll see later on in a little bit. So the ultimate goal, this is some of the original project specifications we had going in. 10 degrees of freedom, remote parallel human interface for familiar and intuitive control. Low cost, research, development, and prototyping. We wanted to aim for under $1,000, which was our allotted funding between 189 units and the Europe funds. And also a fair amount of robustness, which is one of the biggest things we were interested in. So we wanted it to at least, compared to a regular human hand in terms of dexterity, strength, and the temperature melting point of human fingers. So the original specification. I think I got these mixed up. Sorry. So the original specifications that we started out with. No, not bad. The original specifications that we have is 2 degrees of freedom per finger, making for 10 in total, and a public fidelity of within 10 millimeters for the points of interest. I'll be talking about the actual motion tracking later in a little bit. We wanted response time for just under a second, probably, which was pretty easy to meet. We wanted it to be waterproof, so be able to be submerged underwater for 5 minutes without fail, and heat resistant, withstanding a human hand temperatures of 120 degrees Fahrenheit or 48 degrees C, which is the burning point for most human hands. The final build, unfortunately, high dexterity, we got about 2 fingers working, only 1 degree of freedom each. Public fidelity, we never got through the entire evaluation of all the prototypes, but the motion tracking code does work. I have a picture of that, it's kind of cute. But the motion tracking does work. We don't have any comprehensive data. Response time from the puppet to the actual mechanical hand is under 1 second, which is nice. Waterproofing circuit still exposed and uncovered. Heat resistant. It wasn't tested. We didn't apply an actual open flame to it, but according to the specifications for our material, it should be within margins, which I'll touch on in a little bit. Major design features of the robotic hand as a whole. Tendon servo actuation, high density, the tendon servo actuation, which was the model which we actuated the fingers with. I'll just take a look at the tendon servo slide. We were interested in the tendon servo actuation method, which is very similar to the regular human muscle tendon method, right? And so you can see a nice picture of the 3D printed hand over there. There's strings running up all the way to the ends of the finger over there, and those strings are attached to servos which spin and pull the string along with the rest of the finger downward. And so it works, again, very similar to the muscle and tendon model. Disadvantages, definitely the lifting capacity, right? So I mean, it's kind of odd trying to curl a finger using nice lateral motion along the string, but so we chose pretty strong servos to counteract that. And the servos took up a lot of space, and we never quite resolved getting the servos placed around properly. Alternatives that we considered for a while was pneumatic actuation using air, maybe like some plastic tubes or something like that, curl them up, it's like air. Not entirely sure. And hydraulic actuation, pros and cons, high power and strength, of course, so we wouldn't have to worry about speccing that out properly. But cons, it was temperature dependent and pretty complicated, so we opted out of all of those because just the regular tendon servo one is the easiest for us to apply. I was talking about the material that we chose, Doran plastic. Again, it's a pretty high temperature, pretty high yield strength, so between 5K and 11K PSI, and temperature ranging between operational temperature range of -20 Fahrenheit to 120 Fahrenheit. It's convenient. This is plastic. It was a bit stronger than wood. It was a bit cheaper than metal, and we were able to do all the manufacturing in-house because it was high density. So we were able to use traditional shop methods on the Delrin, which was nice for us. Alternatives: 3D printing, metal, wood, like I mentioned. I'll talk about 3D printing towards the end, but I wish we would have looked into 3D printing more. The other big aspect was this puppetilla operation, right? Wanted to be able to operate this hand from a remote location. Like I mentioned, you get this kind of organic control, organic movements with intuitive organic inputs. The cons: it does get really complex if you're trying to model the different degrees of freedom of the hand, which I'm not sure how many there are in total, but there's a lot more than 10 definitely. Again, alternative traditional remote controls with joysticks and buttons or preset configurations. There's some interesting hands we saw that they map the entire hand to move in one particular motion, like one entire grasping motion as opposed to actuating each individual finger. So that was kind of interesting, but we decided to opt out for the individual degrees of freedom instead. This is the Arduino selection. I don't know much about this, honestly. The main difference between the Arduino and the Arduino Mega was the number of analog input pins. So originally it was spec'd out for 10 degrees of freedom, so we needed 10 inputs. But the Arduino, the standard one that we get in our labs and stuff like that, only had 8. The Mega supports up to 16. It also cost about $50, but what can you do? And we were hoping that would leave more room for expansion in the future as well. Concerning servos, I was talking about the actual power required out of these. These are 3 different ones we were looking at. You can see they're pretty uniform across in terms of torque. They have like 10 kilogram force per centimeter. 10 kilogram feet? I'm not actually sure what that unit is. all the servos are about the same though, in terms of power. The main difference was price for us. So the first one, the HT Power MG, was about just under $10 compared to $30 and $34. But going down to precision, you also see that the H Tower Pro was also the lowest in precision compared to the other two. So that was something we'd have to deal with later on. This is a simple schematic of the electronics that we were dealing with. I don't think I covered it all entirely, but we were using a Arduino. We had a servo and we had a flex sensor attached to it. We took inputs from the flex sensor, which were mapped to the Arduino, which resulted in rotation on the servo. You can see over there, attached to the flex sensor near the bottom right, that's actually a voltage divider. If you guys are familiar with voltage dividers, it's just like it's a way of measuring different resistances, and you take a different voltage out, and so then you're able to measure. Sorry, I'm a bit stumbly right now. The main point of a flex sensor is that when you bend it, it changes resistances, and using a voltage divider, the change in resistance can be mapped to a change in voltage, which is read by the Arduino, which is fed to a signal and servo. That's work done so far. We're currently at 3 different iterations at this point. Over on the left, you can see the project as it was last year. 3D printed fingers. They had a pink foam backing, which is pretty fun, and they used these nice like fabric tendons, which is pretty cool. And on the right, you can see some of our work from the previous 2 quarters. It's the SolidWorks design for the last prototype that we had. Those are wooden fingers over there, and that was just some fiberglass on the bottom for the palm. You can see kind of the erratic spacing of the servos over there as well. And on the bottom right, you can see the actual finger curling along with the hand. It's pretty cool. And again, uncovered circuits, dangerous stuff, good stuff. This is the current iteration of the fingers that we have right now, though. That's the SolidWorks up on top. We use these nice little joints that we fit inside of the finger. We like this design a lot because it was fairly robust compared to the previous design, which, again, we had these kind of hinges on the back of the finger, which is kind of odd. So we moved the hinges inside of the finger and stored it in plastic and applied some glue. Again, there's another picture of it working. Good stuff, good stuff. That's the final build of the hand that we had as last quarter. Those are the 5 fingers and thumb. Not exactly fully actuated thumb, but good stuff, good stuff. Yeah, that's Delrin already. This is what I was talking about for the image processing earlier. This is one of the fun things I get to do this quarter. Apparently MATLAB has an image processing suite, which is a lot of fun. And so what we wanted to do is be able to track the actual motion of the fingers, right? So we wanted to compare the actual paths and motion of the robotic fingers compared to the human fingers and those inputs that you're putting in. And so this is just an example of the MATLAB sees. We put these little white circles on there. Those are actually just a whole bunch of pieces of paper. We just super glued them on to one of the original fingers from last year. So yeah, that was pretty fun. I don't have a picture of the final graph. Unfortunately, I didn't save it last time I was playing with that code, but It works fairly well. The MATLAB code, the entire suite, it lets you track circles and images, it lets you track the positions of the centers, and from there you can start extrapolating like distances and lines in the path of the finger itself as a little skeleton model. Moving on, cost analysis. Last estimate that we had, just over $150. And so the main cost of that probably being like the servos and the Arduino themselves. The Delrin is relatively cheap, and we use scraps around the lab when we could. So, well within budget, still have plenty of money to burn, honestly, but moving on, cool. Retrospective, a lot of things I regret. Yeah, so I mentioned it earlier. Originally we wanted like 10 degrees of freedom, but at the end we still barely had 2 fingers working, unfortunately. The original hand from last year was produced using 3D printing, which was interesting. I actually really liked that, and one of the biggest things about, I think I have it over here. No. One of the biggest things that held us up last quarter was the manufacturing of the Delrin plastic. So we spent a lot of extra time. Only one of us actually was certified to work in that lab, and so that took up a lot of time. I wish we would have went to 3D printing because naturally the rapid prototyping aspect is highly desirable. But the problem we did have with that original design was the blockiness of the joints. Right? So they were pretty square and they caught a lot. There's a lot of friction over there. We weren't quite sure how to alleviate that, but we went ahead with Delrin plastic because we were interested in seeing the robust nature of it. Yeah, concerning the actual finger designs, I touched on it a little bit. The current design is kind of nice. It looks a bit more, cool and hip, but it's also a lot smoother and actually moves a lot smoother than the original 3D printed ones did. I mentioned it again earlier. The original model used fabric tendons instead of nylon tendons. The nylon strings were actually really hard to tie, and they kept stretching a lot too, which was unfortunate. And so, like every now and again, we'd pick up the hand again, and all the strings were kind of warped and loose again. We had to tie everything up. But the fabric tendons didn't have that same problem, so should have probably went back to that. We did keep the same tendon servo model throughout the entire process over the past year. Personally, I wish we would have looked into other things, but it is really simple, and I liked it a lot. But it served us pretty well. I'd hope to go forward with it. That all said, the project from a technical standpoint I didn't think was that challenging per se. I think our biggest problems of Strife were probably like our internal organization. So CubeSat touched on it, just organization, mission statement, and stuff like that. I wish we would have had a stronger mission statement going forward, stronger project specifications. Because we often found ourselves, in the middle of a meeting, like I'm not really sure what to do with ourselves right now. But if we, mission statements and project specifications are supposed to motivate those meetings and those discussions. Leadership and organization, we never had like a legitimate, de facto leader. I was technically the project lead, so that was partly my fault. But I always deferred to a lot of other people, so definitely should have taken a stronger stance there. But that said, decisions were pretty hard to implement and enforce. Because no one really recognized an official leader. And CubeSat again touched on it before, but the difference between like the students taking units and just volunteers just showing up to have a good time. Most of our group about like maybe 1 or 2 of our members last year were unitless, and it was hard to get in touch with them. It was hard to actually communicate and get them accountable for different projects and points. I feel like these are all fairly obvious points. You should be organized, you should be accountable. But I thought I was perfectly capable of putting on a project, and here I am. But so just a word of warning to everyone in the crowd. Just calm down. I wish we would have been more organized. I wish we would have had a more motivating mission statement that would allowed us to make better decisions overall. And then I already covered most of this. Define roles, responsibilities. Some references, some of the pictures we took. Any questions? How are you guys doing today?